Hello all, this is Ramesh Lama. Welcome to the video lecture. In this video class, we'll be discussing about the history of computer vision. In recent years, the computer vision has taken a great leap. However, it certainly isn't a new scientific area. Computer scientists and mathematicians around the world have been trying to find the ways to make machines extract meanings from the visual data for about 60 years from now. But I want to start with the work of biologists in late 1950s, which is one of the most influential works in human as well as computer vision, and it was published by two neurophysiologists, David, David Hubble and Thorsten Wiesel in 1959. Their publication entitled Receptive Fields of Single Neuron in Cat's Straight Cortex attempts to find the answer of question, what is the visual processing mechanism in mammals, which is more or less similar to human brain from the visual processing point of view. And what they did was to place electrodes in the primary visual cortex area of an anesthetized cat's brain and then projected patterns of light and dark on the screen in front of the cat. And what they observed is like there were many types of neurons in the primary visual cortex. One of the most important neuron is the neuron which respond to the oriented edges. Hubble and Wiesel called these neurons simple cells. Besides this neuron, there were other types of neurons which they termed complex cells. These neurons detected edges regardless of where they were placed in the receptive fields of the neuron and could preferably detect the motion in certain direction. The core finding of this study was the visual processing starts with the simple structure of visual world, that is the oriented edges, and as the information moves along the visual processing pathway, the brain builds up the complete visual information until it can recognize the complex visual world. The next highlight in the computer vision was the invention of first digital image scanner. In 1959, Russell Kirk and his colleagues developed an apparatus that allowed transforming images into grids of numbers, uh, and it was able to trace variation of intensity over the surfaces of photographs. And one of the first scanned photographs was the image of Russell's infant son, and it was just grainy 5 centimeter by 5 centimeter photo captured as 30,976 pixels with the size of 176 by 176 array, and it has become so famous that the original image is now stored in the Portland Art Museum. The next important work in computer vision is taken as the Larry Roberts' Machine Perception of Three-Dimensional Solid, which was published in 1963 and widely considered to be one of the precursors of modern computer vision. This work is also known as block world. The goal of this program he developed and described in the paper was to process 2D photographs into line drawings, then build up 3D representations from these lines, and finally display 3D structures of objects with all the hidden lines removed. And in 1966, there was a famous MIT summer project called the Summer Vision Project. The goal of this project is to attempt to use the summer workers efficiently in a construction of significant part of the visual system in few months. The students coordinated by Seymour and Gerald Sussman were to develop a program platform that could perform automatically background and foreground segmentation and extract non-overlapping objects from real-world images. It was the ambitious project, and however, the project was not successful to achieve its goal. 50 years have passed. The field of computer vision has blossomed from one summer project to a field of thousands of researchers worldwide still working one on one some of the most fundamental problem of the vision. And we still haven't solved completely the problem of vision, but it has grown into one of the most important and fast growing areas of the artificial intelligence. Another influential work in computer vision is taken as a paper entitled Vision, a computational investigation into human representation and processing of visual information by David Marr. Building on ideas of Hubble and Wiesel, David gave us the next insight of vision. He established that vision is hierarchical, and he introduced a framework for vision where low-level algorithm that detects edges, curves, corners are used as stepping stones towards high-level understanding of visual data. His framework for vision includes the primary sketch of image where edges, bars, boundaries are represented, and next is the 2.5D sketch representation where surface information about depth and discontinuities on images are pieced together, and finally a 3D model that is hierarchically organized in terms of surface and volumetric primitives. Here is an example of his work, like it has input image. First, the primary sketch with the is constructed, then 2.5D sketch is uh, constructed, and finally 3D model is constructed. And around the same time, a Japanese computer scientist Kunihiko Fukushima built a self-organizing artificial neural network of simple and complex brain cells that could recognize patterns, and it was unaffected by position shifts. This network was termed as neocognitron, which included several computational layers. The, the receptive fields of this network had weight vectors known as filters, and the function of this filter was to slide across 2D arrays of input values such as image pixels, and after performing certain calculations, produce activation events that were to be used as input for subsequent layers of the network. This new cognitron is arguably the first ever neural network to deserve the title DEEP. It is a grandfather of today's convolutional neural network CNN. A few years later, in 1989, a young French scientist, Yann LeCun, applied a backpropagation-style learning algorithm to Fukushima's CNN architecture. After working on the project for a few years, LeCun released LeNet-5, the first modern convolutional neural network that introduced some essential techniques we still use in CNN today. And we can see here the program of LeNet-5 detecting the handwritten digits, and LeCun applied his invention in character recognition, and besides that his work resulted in the creation of a MNIST dataset of handwritten digits, perhaps the most famous benchmark dataset in the machine learning. Around the year 1999, lots of researchers stopped trying to reconstruct objects by creating 3D models. Instead, they directed their efforts towards the feature-based object recognition. David Law's work, Object Recognition from Local Scale Invariant Features, also known as SIFT, was particularly one of them. This paper describes a visual recognition system that uses local features and that are invariant to rotation, location, and particularly changes in illumination. These features, according to Law, are somewhat similar to the properties of neurons that is found in the inferior temporal cortex of the brain, which are involved in object detection process in the primate vision. And the computer vision research in computer vision took a great leap forward in 2009 when researchers led by Feifei Li, who is the head of Stanford's Computer Vision Lab, had organized the ImageNet, a large-scale visual recognition competition (ILSPRC), and is a database of 14 million photographs of tens of thousands of types of objects that were labeled by nearly 50,000 online human workers through Amazon Mechanical Turk platform. By training the networks using ImageNet, researchers developed the ability to identify the objects almost human can. Since the inception, the ImageNet challenge has become a benchmark in object category classification and object detection across the huge number of object categories. In 2010 and 11, the IOSPRC error rate was hovered around 26%, but in 2012, a team from the University of Toronto entered a computational neural network known as AlexNet into the competition, and that changed everything. The model, similar to the architecture of Yann LeCun's LeNet 5, achieved an error rate of 16.4%, and this is taken as a breakthrough event in the field of CNN's computational neural network. And in the following years, the error rates in image classification in ILSPRC fell to few percentage, and winners ever since 2012 have always been CNN. As I have mentioned earlier, that CNN have been around since 1980s, so a question arises: why did it take so long for them to become such popular? And basically, there are three factors due to which current CNN explosion occurred. The first one is the availability of vastly more fast and powerful machines now compared to that of 1990s when LeNet was released. And another reason is NVIDIA's parallelizable graphics processing unit, which have also helped us to achieve significant progress in deep learning. And finally, today's researchers have access to the large-level high-dimensional visual datasets such as ImageNet, Pascal, and so on. Therefore, they can train their deep learning models efficiently and avoid overfitting.